There are two ways to think of the inevitable passage of time. Eternalism assumes that the past and future simultaneously exist with the present, creating a 4D hypervolume, and presentism assumes that only the present exists. Since time is such an abstract concept, it's hard to necessarily prove that either belief is true, but presentism does make you think that the past is the past and that you can't change it, and eternalism basically makes you think that your decisions are useless because the shape of time is always determining your past and future. If you're an eternalist, this video is for you. If you're not an eternalist, check out what happens when a math fanatic gets bored, because in this video, we will be switching time and space axes and rotating time. Let's start off simple. I'll be using Desmos 2D graphing calculator to create scenarios, because 3D graphing calculator would probably be too laggy to be useful. I will define x as the x-axis, y as the y-axis, s as either axis, and t as the temporal dimension. 1 unit in any direction is 1 meter, and 1 second is whenever t reaches a number exactly 1 above it. Sliders are weird because they take about 4.15 seconds to get from the lowest number to the highest number, which makes larger domains go by faster. The range of t will be -10 to 10, which means that our objects are technically going 4.81 meters per second in our simulations at default speed x minus t, but we'll assume it's going at 1 meter per second. Now let's get to the basics. This ball has an equation where time doesn't change its position. It goes 0 meters per second, staying forever still. Let's rotate our time axis such that it replaces the x-axis. And the y-axis. Seems boring until you realize what's going on here. Velocity is defined as the distance divided by the time it takes to travel that distance, miles per hour, meters per second, etc. Here, the ball is moving 0 meters every 1 second, so 0 over 1 is 0 meters per second. Since the equation is basically space divided by time, and we've switched the roles of space and time, we can switch them in this equation, which gives us 1 meter every 0 seconds. That's 1 over 0, which is... Yeah, so what you're seeing is basically infinite speed. Cool. Let's go back, but only rotate the scene around the time axis by 30 degrees and see what happens. I thought this object was stationary. Why is it moving 0.577 meters per second left? Well, let me tell you why. Imagine you were rolling a paint roller over a line. When the roller isn't rotated away from the line always appears at the center. When we rotate the roller 30 degrees and rotate our view such that the paint is straight and not the line seems to veer downward. That's what's happening. Since time is moving at an angle, the ball appears to be moving when it really isn't. Our now moving objects also appear to grow wider the more we rotate time away from their reference frame. So, I guess the infinite speed thing has some inaccuracy to it. Let's look at 1 meter per second. Switching around the axes doesn't appear to do anything. That's because 1 over 1 is equal to 1 over 1, so it doesn't move any faster or slower than it previously did. Now at 2 meters per second, switching the axis makes it go 0.5 meters per second. So you should see the pattern now. Rotating time such that the time axis switches with the axis of an object is moving on will make the object move at the reciprocal of the speed it originally was moving at. That means that light speed rotated is actually super slow, but in that case it would actually set the limit of how slow a rotated object can go. These two equations will be used to simulate the elastic collision of two equal mass blocks on a frictionless surface. The one on the left is red, and the one on the right is blue. Like our constant speed experiment, both blocks are moving 1 meter per second, but the catch is that they collide when they hit the middle and so start going the opposite direction. What do you think will happen? Well, let's switch x and t to find out. Okay, two things are happening. Why are there two of the same block at the start and the end? A block is occupying two places at the same time. The reason is because we switch space and time, so the reason should be acquired by switching place and time. The block is occupying the same place at 2 times, here and here. That's why you see two of them. The second weird thing is that the block is just fusing with itself. This is just the 3D representation of it, and you can see a crease right on the edge of both blocks' time block. That's why. No other way to explain it. Combining the previous lemma with the next step in a physics simulation, such as this, you could probably predict what happens when two blocks of different sizes collided in rotate time. Oh, and here's an inelastic collision. Acceleration should be simple. Since we know that moving faster in space makes the objects rotated in time move slower, it can be deduced that the car waiting at a stoplight in this simulation, which then speeds off when the light turns green, will decelerate. In our simulation, the car actually starts moving on the opposite side. Isn't that strange? Well, rotate our graph used to simulate acceleration 90 degrees, which is 2 to the power of t, and see that the side of the graph increases at switches. From this switch, we also get another equation changed. The acceleration equation is defined as a change between speed from a moment before and speed from a moment after. Or, in other more simpler words, speed increases as time moves forward. Since speed is the distance covered in a given amount of time, we can rewrite this equation into the simpler distance per time changing per time, or distance per time squared. That's how its dimensional quality is represented. Anyways, now that we've switched time and space, we're now looking for the time per distance squared, or time per area, which is a strange phrase, but hey, so is time squared. This is what we get when we rotate just 45 degrees. Now let's get into more practical stuff. This is a simulation of a quantum wave. I intended to make it more of a sound wave, but whatever. This is even better for the people smarter than me watching this anyway, so whatever. Anyways, the wave is moving at our standard 1 meter per second with a maximum amplitude of 1 meter. Rotating 90 degrees will give us this flappy thing. Rotating just a little makes our wave flap faster and faster as it becomes less and less wavy. Here's constructive wave interference. Here's it rotated. Here's destructive wave interference. And here's that rotated. Now this is a sound wave. In a longitudinal wave, air particles move back and forth, creating areas of lower and higher pressure. We can also simulate a wave created by two balls colliding. Because of the growing wave's shape when interpreted as a 3D surface, the wave doesn't actually extend from the source. I wouldn't know how this would sound if it were a sound wave, but theoretically an area can be constantly illuminated at enough distance, even if it was a brief flash. Let's see what an orbit would look like. To make this easier for you and I, we will simulate a Sun-Earth-Moon system, which we will then rotate 90 degrees. Technically, the distance between the copies of Earth would be 1 year, since if we assume the Sun isn't moving, then Earth will appear in the same position exactly a year later. That means 31,536,000 meters, with our meter to second switch. But of course, the Earth is moving, so this would be another case of a spherical cow. This red wheel is rolling at 1 meter per second, so it will not deform under the previous rules. The dots on the edge of the wheel will indicate pieces of the wheel. Rotating 90 degrees gets us those dots rotating backwards and going faster every time they contact the ground. The reason why is because each dot stays contacting the ground longer than the other spaces, and zero speed is infinite speed in rotated time. A question arises from these hypotheticals. Can this be used to move backward in time? Well, in theory. Here's a simulation of two balls racing toward the center. When they collide into each other, head first, they turn black and stop moving. Can we rotate around time to stop these two from colliding? Yes, but at a cost. Here we have the scene after a full 180-degree rotation through the X time axis. The green ball that was on the left is now on the right, and the orange ball that was on the right is now on the left. That shouldn't be too much of a problem, though. Let's see if our rotation can save the two balls from colliding. Well, we do see the collision happen, but at least it doesn't happen after the rotation. Go team. I have to include equations in this video, or it's not a math video. A lot of time-dependent equations use derivatives because, come on, when you're trying to define something that's always changing, how else would you? The derivatives of the position vector with respect to time are from first derivative to sixth, velocity, acceleration, jerk, jounce, crackle, and pop. In rotated time, these become the derivatives of the time vector with respect to an object's position. The problem with this is that time is a scalar, not a vector, because you can only move forward in time and no other direction, so this really doesn't have an application. The rotated speed of light, as I've shown earlier, sets the limit for how slow an object can appear to move, and as such, time dilation gets a little weird. Using the equation for defining rotation, the time dilation equation becomes this monstrosity, and rotating this equation makes the observer's time longer and longer until the rotation reaches far enough in which only speeds surpassing the original speed of light yield an actual number, so no absolute zero. Speaking of absolute zero, we can describe thermal energy as this equation, modified to automatically convert to Fahrenheit. This equation sits on absolute zero, negative 459.67 degrees Fahrenheit. And as I rotate time around, absolute zero gets hotter and hotter until we rotate 90 degrees in time, to which it is at an infinite temperature. The opposite happens when our water vapor is at 91 degrees Fahrenheit. It starts off getting hotter and hotter until we have rotated 90 degrees, where we find the temperature is about absolute zero. Suffice to say, if you could rotate time, you definitely wouldn't survive. Now, does this have any applications? Of course not! This is simply just an experiment to see what would happen in a theoretical universe where Eternalists are right. With these tools, I am sure you can simulate a lot of different experimental things, like multiple time axes or Eternalist time portals. I invite you to create your own experiments. Watch what happens when you bend the definition of time to your will, and watch what would happen. Desmos exists, and I bet some of you can code, so go have fun, because hypotheticals are fun to experiment with.